Now that we've talked about Q analogs of chromatic symmetric functions, we can talk about Q analogs of irreducible character evaluations. So recall that Gaucharov proved that for P a 3 plus 1 free poset, the coefficient of the Schur function S lambda in the chromatic symmetric function for the incomparability graph of P is the number of standard P tableau of shape lambda transpose. Now Shereshin and Wax extended Gaucharov's proof to show that for P a unit interval order, so they had to use the stronger assumption of a unit interval order instead of just 3 plus 1 avoidance. With an altitude respecting labeling the coefficient of the Schur function S lambda in their Q chromatic symmetric function is the sum over U a standard P tableau Q to the number of inversions P inversions of U. And now that we know that this Q chromatic symmetric function is the character generating function for the Kaj-Dunn-Lustig basis element CW when W and Sn avoiding 312 corresponds to P, so that is P equals the poset, the path poset of FW. This gives that the irreducible character evaluation chi lambda of CW equals the sum over U a standard PFW tableau Q to the number of P inversions in U. So let's do an example. So we showed that for W equal to 1342, P of FW is the poset 1 less than 2 less than 4, and then 3 greater than 1 but incomparable to 2 and 4. And the evaluation of chi3,1 at the Cartesian basis element equals 5. We found 5 standard P tableau, and those are, we could have 1 and 2 in the first column, and then 3, 4, or 4, 3. We could have 1 and 3 in the first column, and then we have to have 2, 4 in that order. We could have 1 and 4 in the first column, and have 2, 3, or 3, 2. Now, if we count P inversions, then Q to the number of P inversions for each of these is, so here, I guess we don't have any greater letter followed by smaller letter, so Q to the 0th. Here, 4 comes before 3 and it's greater. And it's incomparable in the poset, so that counts as 1 inversion. Here we've got 3, 2. 3 and 2 are incomparable, so that counts as 1 inversion. Here we have 4, 2 and 4, 3. 4, 2 doesn't count because 4 is greater than 2 in the poset. But since 4 is greater than 3 as integers and they're incomparable in the poset, that counts as another Q to the first. And then here we have 4, 3, 4, 2, and 3, 2 possible. 4 and 3 are incomparable, 4 and 2 don't count, 3 and 2 are incomparable, so that's Q squared. So that means that chi3,1 of the Cartesian basis element with Q in there equals 1 plus 3Q plus Q squared. The end.